There is a formula for cardinal numbers when you're trying to calculate the number of elements in a union between two sets. Number of elements in the union between two sets. And the formula is this. So you take the number of elements in A, and then you take the number of elements in B, and then you don't want to doubly count the elements that are in both, so you subtract out the elements in the intersection. So let me show you how this would work. And I will just use A and B here. Let me define a couple of sets, A, B, C, D, and let me call B the set C, D, E, F, G. So this is a new example. Okay. And what I'm going to do with this example is I'm going to show you why this formula works right here. So what we need to identify is we need to identify the number of elements in A. How many elements are in A? Hold up your hand. How many?
4.
4, thank you. And how many elements are in B? N of B is?
5.
5. Okay, now when we put these two together and we do the union, we define the union a little bit where we're just going to group all the elements together. And so if we take A and B and we do the union, remember that's kind of putting them all together as opposed to looking at the elements that are in common, that's the intersection. The union is just putting them all together. So if we were to list all of the elements in both of those sets in the union of those two sets, we would have A, B, C, D, there's C, D, and then we would have E, F, and G. This would be the union. How many elements are in the union set? 1, 2, 3, 4, 5, 6, 7. So notice that if we just added the number in A and the number in B together, we would get 9, but that's not equal to the number in the union. And the reason for that is that these two elements, C and D, we don't want to count them twice. That's why this formula says we're going to subtract off the number in the intersection. So here is A intersect B. That's the number of elements that are common to both. And the number of elements common to both would be the CD. I don't know why I circled that one. So C and D are in both A and B, so they're in the intersection. So how many elements are in the intersection?
2.
2. So do you see how these messy symbols here, whenever you have the N there, that just means you're counting up a number of elements. So yeah, it's 2. And thank you all for writing down answers in the chat. All right, let's just apply this now. If we were looking for the number of elements in the union, let's say that this is what we were looking for here, we would take the number of elements in A, which is 4, and then we would add that to the number of elements in B, which is 5, right there. And then this subtraction sign here, we take the number of elements in the intersection, which is right here, 2. So the number of elements in the union is 9 minus 2, or 7. So we could calculate the number in the union without actually doing it by hand. But I wanted to show you that this is why that formula works. If you looked at the Venn diagram representation, we know that C and D are in the intersection, so C and D go in the middle. Also in A are A and B, and also, so if you look at the big circle A, you can see A, B, C, D are in the big circle A. And over here in the big circle B, we have C and D, but we also have E, F, and G. So this is what the Venn diagram would look like for these two sets. I'm trying to show you a different representation of why this formula up here at the top works. So if we just add the number of elements in A, we get 4. And if then we add the elements in B, we get 5. But if you'll notice, this middle chunk in the intersection was counted twice. We don't want to count it twice, we only want to count it once. So what we're going to do is we're going to subtract the number in the intersection. And that's 2. And that's how we get the number in the union. All right, so I wanted to kind of illustrate that formula a couple of ways. We're going to be working with Venn diagrams for most of today. So I'm going to be drawing a lot of pictures like this. We're going to start off with sets that have just 2 sets, or problems that have 2 sets, and then we're going to move on to problems that have 3 sets. All right, I'd like to work through a couple of problems on this worksheet, and then I might ask you to do some as well. All right, so we'll start off with A intersect B. Here's the set A. A contains the elements A, G, and H, and then the set B contains the elements B, G, and H. Now, last time I introduced the operations on sets, and you know that the upside down U means intersection, and that means you're looking for all elements that are common to both set A and set B. And what elements are common to both? Yeah, so when I pose a question, if you'd like, you can answer it in the chat. And yeah, it's G and H. So the answer to this one is G and H. A is not common to both, it's only in one set. B is not common to both, it's only in one set. G and H appear in both sets. That's intersection. Now the next one, this is our fancy notation, but we've already calculated the set A intersect B, and there it is. Now that little symbol in front of it means we're going to count the number of elements in this set. Now that set is not just number in A, it's the number in the intersection, but here's the intersection. So what's N of A intersect B? So number of elements in the intersection of A and B. So here's the intersection of A and B. How many elements do you see there? 2. So that's it. Now the union. The union is, now notice this one says the set A union the set B. So the answer is a new set that contains the union of all the elements in A and B. So we're going to start off with A and G and H. The union has to contain all those elements, but the union also has to contain all of the elements in B. So it has to contain B and it has to contain G. Well, G is already listed there as one of the elements, so I don't want to list it twice. And H is already listed as one of the elements, so I don't want to list it twice. So this is the union. Similarly, for number 4, the number in the union. And since we just identified the union set, this basically takes one more step and asks the question, how many elements are in that set that we just calculated? And you count them up, and you get 4. Okay, let me give you a minute to do 5 through 8. 5 through 8. And then 5 through 8 uses the sets B and C. But same problem, different set. So write down the answers here, kind of using what we did as a model. Okay, let's take a look. B intersects C. Common elements, looks like there's a B. And I guess that's about it, right? Just the B in common. I don't see G in this set, and I don't see H, so I guess that's it. And of course, that's just one element. The union, we have B, C, D, E, F, And so B's already there, GH. And these elements, you can write them in any order. Remember, you don't want to have two of the same because we can write it more efficiently, and those elements can be written in any order. Just group the two together. And then for the number in the union, so how many elements are in that set right there? Count them up. 7. Okay, do you have any questions about that example? Now we're going to do a similar problem, but in this case, instead of using this information, we're going to have a Venn diagram. And to get started with the Venn diagram, I want you to think about a couple of sets. As you look over all these problems, you see, A complement, you see B complement in places, and, some of the similar problems that we had from up here. So the complement is introduced in this one. Now, before I get to those problems, I'm going to draw a Venn diagram for these here. Now, the universal set is the big box, so it has to contain the elements A, B, C, D, E, F, G, H. We know that A and B, when they intersect, A and B, they have to have the two elements GH in the middle. And then A goes with A, so inside the A circle we see A, G, and H, A, G, and H. Inside the B circle we have B, G, and H. And then finally, set C, I'm going to try to draw that one in here. G contains B and C and D, and it doesn't look like A and C have anything in common. No A's, no G's, and C's. So I'm going to write C over here. C contains B, but C also contains C, D, E, and F. So it's a little tricky sometimes, but you can draw a Venn diagram that represents given sets if they're simple like this and small, like 3 elements or 5 elements or something like that. And if you'll notice, A, B, C, D, E, F, G, H, all of the elements from the universal set are somewhere in here. So it's a useful skill to go back and forth between the set notation and the Venn diagram. In fact, you can choose the one you want to use if one's easier for you. All right, so in this problem down here, we're starting with the Venn diagram. And it takes a little bit of, instruction to know how these work. So what I'd want you to do is I want you to identify the set A, list all the elements, list all the elements of B, list all the elements of A complement, list all the elements of B complement. And while you're at it, list the elements of A intersect B. I guess that's problem number 9. And we have A union B there. So let me cross that one out. So go ahead and write down the elements of those sets. I'll give you, again, 1 minute to do it. What I'm after here is something that looks like this up here. So have A and then list the elements of A, B and then list the elements of B, and so on. The difference is that we don't have a set C here. Oh, while you're at it, list the elements in the universal set. I'm asking you to do this because there's one error that a lot of students make a lot, and I want to make sure that you don't make that error. Okay, here's the error that I wanted you not to make. I didn't want you to make this error and just say that A was 1, 4, because A represents this whole circle. And not only is the numbers 1 and 4 in there, but also the numbers 3 and 7 are inside A. So the set A consists of the elements 1, 3, 4, and 7. In a similar way, B contains the 2, 5, 6. We can see that, but the 3, 7 is in the intersection between A and B, so it's also in, those two elements are also in B. So we have to add the 3 and the 7 here. Now, when you do complement, and you have a Venn diagram, it's important that you list all of the elements that are not in A. So I'm going to basically put my thumb over A, and all of the elements that you see remaining, that's A complement. So we have the 2, 5, 6. You can see those there. Those are the elements that are in B, but also this 8, 9 off to the side that's not in either A, or those elements are not in either A or B, but they are in the universal set. So they do make up part of the universal set. And then B complement, similarly, I'm going to just cover up all the elements in B and write down all the elements that remain. And the elements that remain are 1, 4, 8, and 9. In the universal set, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. All the numbers from 1 up to 9. Okay, so far so good. The point is, if you can do the problems up here, like this, if they're in this notation, and you get a Venn diagram, you can always write each of the sets down here, and then it would be just like our previous problem. All right, let's go ahead and write down some of the answers here. I guess I want to do some of both columns. So A intersect B. You know, I think it's easier to just look at the Venn diagram to find the intersection than to figure out what elements are common between A and B down here. You can see that 3 is in both sets and 7 both sets. Up here, you can see 3 and 7 inside the intersection. So however you identify the intersection, I think it's easier in the Venn diagram than, let's write that. And there are 2 elements in that intersection. So it's kind of similar to the first one, where I ask you to list the elements of the set, and then I ask you to identify the number in there. Now, for the union would be, we're going to put all the elements of A and B together. So all of these elements here. It includes everything in the universal set except for the 8 and 9 outside. So this one would be 1, 2, 3, 4, 5, 6, and 7. The 8 and the 9 are outside the union. They're not in either one of those 2 sets. And the number there, if you just count them up, you get 7. All right, the next column is where it gets a little tricky, but it's not too bad. I'm going to show you both how you get the answer from the sets and how you get the answer from the Venn diagram. So A complement is right here, and B is right here. That's why I asked you to write down A complement, because it was in part of the problems. All right. Now, this operation is intersection. And so we have our 2 sets here and here. The intersection means we're looking for elements that are common to both A complement and B. So which elements are common to both? 2? Yes. 5? Yes. 6? Yes. 8? No. 9? No. So 2, 5, 6 are common to both. And the number of elements in that set in number 13 is 3. So we're going back again between listing the elements and identifying the number of elements in the set. Okay, go ahead. You try number 15 and 16. B complement, there. A complement is right there. So now you're focused in on these 2 sets. And the other thing that's different is you want to identify the union as opposed to the intersection. So you have a different set operator there. Now, if your problem were this, B complement intersect A complement, then when you look at A complement and B complement here, you can see that the elements that are common to both are the 8 and the 9, and they don't have anything else in common. So if your problem was find the intersection between A complement and B complement, the answer would be 8, 9. In your problem, you're looking at the union. So what you do is you take all the elements in A complement, 2, 5, 6, 8, 9, and join that with all of the elements in B complement. So 1, 4, 8, and 9, and 8 and 9 are already listed there, so we don't list them twice. And if you count up these elements, you have 1, 2, 3, 4, 5, 6, 7. Now here's kind of an application. You may see something like this. The set A contains 12 numbers and 18 letters. So the number of elements in A is what? Imagine you have a set. It contains 12 numbers and 18 letters. How many elements does it have then? Yeah, thank you, 30. Because elements in a set are either numbers or letters or symbols. They can be anything. Okay, read the next sentence. The number in B is what? B is a set that contains 14 numbers and 10 letters. Think of the numbers 1 through 14 and the letters A through, I don't know where the 10th letter is. Yes, okay, very good. 24? That's correct. Now, the next one says, the next sentence says, one number and 6 letters are common to both sets. What they're trying to describe to you there is the number in the intersection. If we have one number and 6 letters common to both, so how many elements are in the intersection then? The definition of intersection is, you know, elements that are common to both. And here they say there's one number and 6 letters. Get the idea? All those 7s? Yeah, number is 7. So you can see how we're, you know, kind of making connections and making sense out of intersection and union, using things like common to both and joining them together. Okay, then the question. Find the number of elements in set A or set B. And what they're looking for is the number of elements in A or B, and or is the word we use for union. The word that we use for intersection, I'll just write it here, is the word and. Number of elements in A and B. And by using the word and, we mean both, in both. All right, now I'm going to show you what you use, the tool that you have to use in order to solve this problem. And it's right here. This was the very first result that I gave you today. And here's the formula that relates those 4 numbers in that other problem. So I'm going to rewrite this formula, and then we're going to come back and answer. The number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersect B. That was the formula from the previous page. And we've just, from reading this problem, we have identified 3 of the 4 numbers that we need in that formula. So I'm just going to write the number in A, you told me was 30. The number in B, 24. And then the number in the intersection is 7. And we're looking for the number in the union. So all we have to do is to add those 2 numbers, 54, and then subtract 7. And I guess that's 47. Now 1.4.6. We're going to be using the same tool, so I really don't have any new formulas to give you, new results. It's just that the Venn diagrams that we create and the problems that we do just get bigger and more complex. But the idea here is just to break down these big problems into smaller parts. And if you can do that, then you can do these problems. So maybe we'll begin with the Venn diagram problem down here. So what you're going to see in this section are 3 sets instead of just 2. And it makes the problems a little bit more complicated. The other thing I want to remind you of is that our book uses complement to be the little superscript C instead of the apostrophe. So I'm going to change those two problems to a superscript C instead of a. Okay, we're going to start this one like we did the others. We use the set A, and we use the set B, and we use the set C in some of these. And so it's important to be able to read from the Venn diagram, as well as if it's easier for you, then you can actually write out the elements in each of the sets. Now, for example, I wouldn't necessarily write this out. I would just say, oh, for 34, they want me to list all of the elements of the set B. So I would say, well, that would be all of the elements inside the B circle. And here's the B circle. So not only do we include the 10 and 11 that kind of that's hanging out there by itself, but there's these other numbers, 4 and 5 and 6 and 9. All of those numbers are in B. So the elements of B are 4, 5, 6, 9, 10, and 11. Now they don't ask us for A here, but I'm going to write A as well. A is this set here. 1, 2, 3, 4, 5, 6, 7, 8. You'll also notice in this set, you don't have any cardinality numbers in here. They're not asking you for the number of elements in the set, just what are the elements in the set. B we wrote down already, but I'll write it again. Okay, C is this set down here. So I see inside that C circle, that C set, we have 6, 7, 8, 9, and 12. And the last one is a universal set, and I'm just going to look at all of the elements in the rectangle. So most of them are inside the circles, but the element 13, sorry about that, we've got some weird sun going on here. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so all the numbers between 1 and 13 inclusive. Okay, keep looking in the chat. In case you have any questions, you still can ask questions at any point. You know, how did you get that? Or I don't understand why 7 is in the set. Other questions. So please feel free. I want you to understand as we're going through this. Okay, B union C. Now, when I look at B union C on the Venn diagram, here's B and here's C. So I want to combine all those elements together. So I'm going to shade it. Here is B union C, all of the elements that are shaded. So if you look at all of the numbers that exist in those regions that I shaded, you can just list them all. Looks like the smallest one is 4, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. So you can look at the Venn diagram and find the answer to the question 36. But you can also just take B and C in this notation and list down all the elements. 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now 38, you can use number 36 to answer number 38. Look how they're common. 36 says find B union C, and 38 basically says find the complement of that. Find the complement of B union C. Now the complement means all elements in the universal set that are not in the original set. Since we've already calculated B union C, let me show you a way that you can find the complement of that. You can list all of the elements from the universal set, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. That's the universal set. If you know B union C, the complement of B union C, what you do is you just go through the universal set and cross out all the elements from B union C. Everything that's left is in the complement of B union C. So I'm going to cross out all the numbers 4, 5, 6, 7, 8, 9, 10, 11, 12, 4, 5, 6, 7, 8, 9, 10, 11, 12. And all of the elements that remain, those are the elements in the complement. So 1, 2, 3, and 13. So what we're doing is breaking down these big expressions into using, going back and using our definitions. Okay. Now we're changing operations. We're now going to intersect. And again, for me, I look at the Venn diagram and it's easy for me to see because I know where the intersection of A and C are. Here's A and here's C. So the intersection is in this region right here. If you have a set that doesn't involve B, just imagine that B is not even in the picture and just draw A and C. It's this blue shaded region here. And the elements in there are 6, 7, and 8. All right, number 42, we're going to, not only can we have a union between two sets and we're going to join just all the elements of the two sets, we can also have a union of three sets where we take all the elements in A, dump them in, all the elements of B, dump them in, and all the elements of C and dump them into our new set, and just get rid of the duplicates. On the Venn diagram, the union of all the three sets would consist of all of this. Everything inside the three sets. If an element is in one of the sets, then it's in the union of all three sets. Union is joining. So I'm going to identify all the elements in the three sets together. And I think it involves everything except for the 13. So 1, 2, 3, 4, 5, 6, 7, all the way up to. So Tasha asked, can you use the method 1, 2, 3, ... up to 13 for the universal set? Yes, absolutely. Yeah, but it looks like some of you are picking it up. And the reason why some of you are coming so quickly to the answer is that you recognize there's a relationship between 42 and 44. So 44 is just the complement of the answer in 42. So if you struck out all those elements from 42, 1 through 12, the only element remaining in the universal set would be 13. Now, there are some problems like this one here where we're going to be using Venn diagrams again, but we are going to just do some shading instead of writing down elements and listing elements with the roster method. We're just going to shade the Venn diagram. So let me show you how that works. Over here, we're going to shade A complement intersect B complement. And over here, we're going to shade A union B complement. And what this problem involves is, you shade the one set, and then you shade the other set, and when you're done, you want to confirm that the two shadings are equal. And that's how you show that one set is equal to another that involve complex results. Okay, here's A. So what I'm going to do is I'm going to graph this one right here. A complement intersect B complement. I want to shade this one. But I'm going to use a worksheet down here to show you how it happens, how it occurs. The first thing I'm going to shade is A complement. Now A complement is everything outside the set A. So I'm going to shade everything outside the set A. And specifically, I'm going to shade everything in the universal set except A. Notice that everything is shaded except the circle A. That's how we shade A complement. Now I'm going to shade B complement. B complement is everything outside of B. So here's B, and I want to shade everything outside of B. I'm going to act as if A is not even in the picture, even though we know that it is. So what we have here is we have two different color shadings. We have the blue shading and then the red shading. Now we want to go to our answer. What is the answer? And because the operation is intersection, we're looking for all those regions that occur in both of those two sets. On my shaded Venn diagram, it means all of those regions that are shaded twice, all of the regions that are shaded in both blue and red together. So on the answer here, this is my worksheet. If you look at all of the regions that are shaded twice with blue and red, it's everything outside both circles. This region here is only shaded in blue. This region here is only shaded in red. And this region in here is not shaded at all. So the region that is shaded both times is the area outside both circles. So that's what the answer shading would look like. It's really, I just transferred the doubly shaded region here up to my final answer. All right, now let's do the next one. Let's do this one over here. Now, A union B would be all of this. Everything, we're going to join together the set A and the set B. So we would shade all of A and B, including the intersection of A and B. But we wouldn't shade anything outside the intersection. Now, if we took A union B and took the complement, that same blue set, but then we took the complement, it would be everything outside the blue shaded region, everything that's not the blue shaded region. So it would be all of this. So I'm going to transfer, this is my worksheet. I'm going to transfer the answer up here. The answer we want is A union B complement. That's the red shaded region. So if I shade it up here, the red shaded region from my worksheet is everything outside both of the circles. And this is how you can confirm that it is the case that A complement intersect B complement is equal to a union B quantity complement. Notice the two shadings are the same here, so therefore these two sets are the same. Even though they look quite different, they turn out to be the same. So you'll have some problems like this where you verify that two sets are equal. These other ones will take some practice, but here's what the problem is. If you were given the region, could you come up with a set that describes the region? That's what they're going to ask you to do. In fact, this one here is exactly this set. So we could either write this answer as A union B complement or A complement intersect B complement. So what this problem is asking you to do is to start with the shaded region and then come up with the set notation to describe the shaded region. Anybody want to take a shot at 74? Use the set A and B and maybe an operation like intersection or union and try to come up. And here's what you want when you're done. Just this little slice of B, not all of B, but just this little slice of B. Does anybody, can anybody tell me, it would be hard to write in the chat. It might be, you could probably write in the chat if you want to use intersection to be the, intersection is the downside U. So that might be a difficult one. All right, let me just go ahead and give it to you. If you take the set B and you intersect that with A complement, this is the set that you'll get. A complement is everything outside of A. Just imagine that you've shaded everything outside of A, and then shade the B circle, and then take the intersection and look for the doubly shaded region. Okay, we are currently out of time, and so I want to stop here. We did not get to the problems from section 1.4.7, so when we come back, we'll review these Venn diagrams and and give you some chance to practice. What you should do is go and try the problems from section 1.4.1 all the way up to 1.4.6. And do all those problems. Bring your questions next time. Remember the earlier problems, the ones that you practiced on in groups now, 1.1 up to 1.41 up to 1.44, those are all due on Wednesday night before our next class. So no class on Tuesday, and homework due on Wednesday night, and we meet back here on Thursday. So have a nice weekend and nice holiday weekend, and we'll see you back here next Thursday. Of course, I'll hang out in the chat room for a while in case you have any questions, you want to go through something, and we can do that. Otherwise, class is ended. You can hit the leave button, and we'll see you here next week.